Okay. Let's wait a minute. Extension field. Okay, let's get started. So today we'll go more into algebraic elements. We'll do some problems with it, just so you're all comfortable. So let E be extension field of F. Then let alpha be an E. Then we have an evaluation map, right? Phi alpha from f of x to E, given by, you just send the polynomial x, you evaluate it at alpha, right? Or maybe let's not use F, let's use P. Yeah, so case one, if you are algebraic, right? If alpha is algebraic, then kernel, then we proved that, kernel of alpha is generated by that unique irreducible polynomial, right? So you see that the image of phi by first isomorphism theorem, or if you like fundamental homomorphism theorem, this thing is isomorphic to f of x quotient, the kernel, right? Which this side is a field, right? Because this is irreducible. So basically there's a name for image of phi alpha. So this is the smallest subfield of E containing F and alpha, right? Because certainly F alpha is in there, right? Because I mean, quite frankly, X maps to alpha, right? So certainly, we have that. So we will denote this as F of alpha. And so later on, we'll basically see how this field looks like. So there's a theorem that describes this, but this is what we call F of alpha. It's just image of phi of alpha in the evaluation map. Now, case two, if alpha is transcendental, this part's easy because if you're transcendental, you're not a root of any polynomial, right? So what's the kernel in this case? Yeah, zero, right? If something else was in the kernel, then that means some polynomial has it as a root, right? So kernel is trivial. Kernel of phi of alpha is just zero, right? So in that case, the image of phi alpha is isomorphic to f of x quotient the kernel, but this is just zero. So this is just isomorphic to f of x, right? Everyone clear? So we sort of so this thing in particular is an integral domain, right? Because f of x is, I agree, is not a field yet. So we define f of alpha in this case as the field of fractions of f of x. And you sort of know how this looks like, right? So if there's no kernel, right, what does this map do? I'm sending polynomials, like polynomials in x, right? And then I evaluate that. So I get polynomials in alpha, right? In the transcendental case, right? And there's no relations, right? Because I mean the kernel's trivial. So it's just all so think of, you know, image of phi of alpha as like all polynomials in alpha, right? And then the field of fractions is just quotients of polynomials, right? It's like polynomials in alpha, right? Over like Q of alpha. Yeah. So these are elements in here. So this is for the transcendental case, right? Everyone clear so far? So there, it is stated without proof, but pi, e, these are transcendental numbers. Transcendental numbers. The proof is actually really difficult. Dental numbers over Q. Yeah. So, okay, let's continue. So there's a name for this. So an extension field E of a field F is simple extension of F. If E is what I wrote before, F of alpha. Yeah. For some alpha and E. So now the you know, I told you how F of alpha looked like in the transcendental case. So the next step is in case one, how does F of alpha look like? So again, I define F of alpha as this for the transcendental case, and then as this for the algebraic case, right? So how does it look like, right? In case one. So there's a theorem in your book that tells you, but it should be quite easy. Be a simple extension f of alpha of a field F. Alpha is algebraic over F. And we're gonna let n equal the degree of the irreducible polynomial of alpha. Yeah, over F. Then if beta is in, so if I take an element in F of alpha, right? Beta can be expressed uniquely as basically combinations of alpha. Yeah, but up to n minus 1, where bj is in F for all j. So this is actually clear, right? Because if you go back, right, the image of phi was isomorphic to like f of x quotient, the thing, right? So if you go back here, right, the elements in image of phi are just polynomials in alpha, right? But there's a relation, right? Some of them it gives 0. Agree? So, but we know the smallest one that gives 0. So if like, so if I write here, right, in this case, like this thing, it's polynomials in alpha, right? I mean, you're just replacing x with alpha. So before you had a polynomial in x, now you could think of it as a polynomial in alpha. But some of it gives 0, right? So if I denote this as I think I wrote it as degree n, right, plus an minus 1 x to the n, because it's monic, right? I could rewrite all x to the n terms. So I know alpha, when I plug in alpha, this is 0, right? So I know, let me replace this with alpha. So I know this is 0 because alpha is a root of it. So in particular, alpha to the n is negative an minus 1 alpha to the n minus 1 minus the dot minus a naught, right? So a alpha to the n can be rewritten as lower powers, as like linear combinations of lower powers of alpha, right? So now you see that all polynomials in alpha are of degree n minus 1 or lower, right? Because if I had like this thing, I could just keep doing it inductively, right? Like if I had alpha to the n plus 2 plus 1 equals 0, for example. Well, alpha to the n plus 2 is alpha to the n alpha squared, right? Plus 1 equals 0. Alpha to the n, I could rewrite using this, right? So, you know, I don't want to do it all the time, but hopefully you get the idea, right? Plus the dot alpha squared equals 0. So now my power went from n plus 2 square times n minus 1 is n plus 1, right? Negative. I'll just focus on this term, right? So this is alpha to the n plus 1, right? When I multiply by alpha squared. And now n plus 1 is alpha to the n times alpha. And then I can rewrite alpha to the n again as whatever is in here, right? And then you just keep doing it inductively, right? It's kind of like how I told you, right? If alpha squared plus 1 is 0, then alpha squared is minus 1. Then I could change like alpha to the 4th as alpha squared times alpha squared, which is negative 1 times negative 1, which is 1. So same idea here, right? But this is like in general. So does everyone see that I could like reduce everything to like lower than the degree of this thing? Okay. Well, then that's exactly what it says, right? I mean, the proof, they just have to prove uniqueness, but like, you know, that's the idea, right? You could reduce to everything of degree lower than the degree of your generator, than the degree of, well, than the degree of this thing. Okay. Everyone clear on this? Why do I have erase? Yeah, okay. So for the rest of this class, we'll just be doing problems, just so you know, you all see how to use definitions. And then we will call it a day. So 29, let E be extension field of F. Let alpha, beta be an E. Suppose alpha is transcendental over F, but algebraic. over f of beta. Show beta algebraic over f of alpha. So, any ideas? So alpha is transcendental over f, so it can't be solved. Now, no, nobody. um. Okay. So how about this? Is beta, so there's two, let's split it to two cases. Beta is algebraic over f, and case one, beta algebraic over f, and case two, beta algebraic over, transcendental, sorry, transcendental over f. Yeah. So I claim in case one is easy. So if beta's algebraic over f, what it should be a one-line proof. So why is beta algebraic over f of alpha? Uh, you all seem confused. So here, let me ask you a question. What is f of alpha? Does f of alpha contain elements in f? Let me ask you that. Forget this problem. Does it contain elements in f? Okay, that I'm claiming that that is all you need to know. So you're that is really all you need to know. So for case one, right? So I want to show it's out. What does it mean that beta is algebraic over f of alpha? Can anyone tell me? Like just definition. Like what is it I want to show? Like what does it mean when beta is algebraic over f of alpha? Like just definition. Not f of x. So it means there is a polynomial in f of alpha of x, right? Such that, beta is a root, right? So there exists a polynomial in here such that beta is a root. It's over f of alpha, not over f, right? So, okay, so now what you said here is what, if I'm algebraic over f, I know there exists f of x in f of x such that f of beta is 0. Does everyone follow? Like in case one, this is what it means to be algebraic over f, right? Okay, why am I done? Like, why did I say like if f of alpha contains elements in f of x, if f of x belongs to f of x certainly belongs here, right? And then you're done. Yeah. Because elements in f certainly belong to f of alpha. So this part's easy, yeah? Because I could just think of this f as an element in here. Does everyone see this? Right. So in general, like if you are algebraic, like how about this? Let's take E. If beta in E is algebraic over a field, forget like any field, like a field F, then it's algebraic over F prime if F prime is bigger than F. Yeah, that's always the case, right? Because I mean, just think of an example if it's confusing. If you're algebraic over Q, you're algebraic over R. That's pretty much what's going on here, right? Because if there's a polynomial in Q, then algebraic, there's a polynomial, let's say, let's just make it up, right? X squared plus 1/2 x or plus 2, right? Like, let's just say beta is the root of this, right? Then beta is certainly algebraic over R because you just take the same thing. Yeah, because if these are in Q, these are also in R, right? Because R is bigger. So I could regard this as an element in R of X. And wow, this is an element of Q of X. Does everyone see this or understand the argument? Yes. No. More like this, Jacqueline. This is in you need the of X, right? But yeah. So again, kind of like this is the think of this as like your F, and this is like your F prime. Yeah. That so all you need to know is F of alpha contains F, and then you're pretty much done. Okay, does everyone follow? So this is the easy. That's the easy case. So if you don't understand the easy case, please speak up. So okay, I will take no comments as we're good. Okay, so if beta is transcendental over F, can anyone describe to me F of beta and F of alpha? I went over this in the beginning, right? Since they're both transcendental over F, how do their field of fractions look like? I mean, how does this field look like? It looks like these are like rational functions in beta, right? This is like rational functions in alpha. Does everyone remember? Right here. Yeah. So when you're transcendental, you're like, you sort of behave like an indeterminate. So okay. Now what does the question tell me? Alpha is algebraic over F of beta, right? So there exist polynomials, right? So what does it mean? There's a polynomial in f of beta, but I sort of know how elements in f of beta look like. It's like something like this, plus p1 beta over q1 beta, right? So alpha, where alpha is a root, right? So, you know, p minus 1 plus alpha to the n. Does everyone agree? So this is just definition of alpha algebraic over f of beta. Does everyone agree? I'm just writing elements in f of beta like this because I sort of know how they look like. Okay. So what do I need to show? So I need to show the opposite, right? Beta is algebraic over f of alpha. So I need to show, like, you know, kind of reverse the roles of beta and alpha, right? And that's exactly what we're going to do. So let's multiply by common denominator, right? So let's multiply by q naught beta qn minus 1 beta, right? So if I do that, I'm gonna get, I'm just gonna write p0 prime for the new thing plus p1 prime beta. So I clear denominators, yeah? Alpha plus pn minus 1 prime beta plus, but now I have pn prime beta alpha to the n. Well, where did my alphas go? N minus 1 equals 0. Does everyone understand what I did? I mean, all I did was just multiply by this thing. Q not, I multiplied by the common denominator. How about that? So, and then I just get a new set of stuff. Is everyone good on this? Okay, well, at this point, we are pretty much almost done. The only thing left here is to say, okay, well, let's sort of combine terms, yeah? So what I'm going to do is I'm going to combine like the powers of beta whenever appropriate, yeah? So what I mean is, let me think of how to write this. Yes, so that seems valid. So for example, if this thing right here, you put in green, was like, you know, beta to the n plus the dot, yeah? Plus, you know, if this is the highest degree, because these are polynomials now, right? And then this thing is like, I don't know, beta to the m plus beta to the n. And then some, I mean, it could have constant terms, right? But I'm saying combine all the same powers of beta. Yeah? Does everyone get what I mean? And then like, so foil the alpha in, but then you combine all powers of beta. Yeah. So group all the powers of beta together. So for example, let me just do an example. Like if this thing was like beta squared plus, I don't know, beta plus 1, and this is beta to the cube plus 2 beta squared plus 1. Then when I group it like this. So beta cubed, so this alpha beta cubed plus the beta squared here is 1, so 1 plus 2 alpha beta squared. So combine the beta squared terms, and then combine the beta terms, and then combine the constant term. Does everyone see the idea? What I mean? Like group all the beta powers, like, yeah. So from there, like, so let me just say group all beta power, constant beta terms, group all beta terms. And then what you're gonna see is you're done. You get like a polynomial. I'll call it a prime, a0 prime. Yeah, I just put a0 prime plus a1 prime beta plus a2 prime beta squared plus a3. I'll just stop at like k. Yeah, beta to the k. Now, where do all these coefficients lie? They have like whatever, these just have like constants, linear combination of like constants and like alphas, right? So this is like linear combination of like stuff with the form like alpha to the I. Does everyone agree? And like constants. Does everyone agree with this? Like here it's like 1 plus 2 alpha, right? And then so it's like a polynomial in alpha, if you like. And that certainly belongs in here. Yeah, because this is like rational functions in alpha. So you see here that like yeah, so you see here that hey, like this thing is so beta, so it shows beta is algebraic over f alpha. Yeah, because all the constants here lie in f of alpha. Yeah, so this question is just like regrouping terms, if you like. You have terms in alpha, right, in powers of alpha, and then you just regroup to term into powers of beta. You're sort of swapping them. Is everyone clear on this? I don't know how better way to explain it. Oh, you mean case 2? By second part, you mean case 2? Yeah, like I mean, that's really where the hard part comes. Like case 1 is like one line, so that's maybe that's why you're uncomfortable. Okay, so let's continue. So here, it's just definitions, right? All I'm doing is using definitions. So let's do another question. Let's go work faster. Well, if you are algebraic, I mean, f of alpha, right, is, I mean, you don't really need to know how they are related, right? Like, all you need to know is this thing contains f. That's really what we're using here, right? If alpha is transcendental over f, this thing, like, this thing is just rational functions in alpha. So this is like a p of alpha. Elements in f of alpha look like this, right? So I could just take q of alpha to be 1, yeah, and this thing to be just a constant like a, right? Let's not use a. I mean, my a's look like alphas. let's take it to be like a constant b in f, right? This is certainly a polynomial in alpha, right? Because I could write this as b plus 0 times alpha plus 0 times alpha squared plus 0 times alpha cubed, so on and so forth, right? So this is certainly, so you see like elements in F are certainly in there. uh, does that make more sense? Okay. Okay, find subfield of R such that pi is algebraic of degree 3. Yeah. Subfield F of R, sorry. So remember I told you pi was transcendental over Q, right? That was one of the things I told you, like it was done without proof. But being transcendental over Q, like it's possible to be algebraic over a different field, right? So obviously F cannot be Q, right? Because I just told you like pi is transcendental over Q. So you need something bigger. So what field do you think we should consider? Like, how about no. The irrationals are not a field. Yeah, it's Q adjoin something, but adjoin what? So I need a degree 3, right? So I need pi to be a root of x cubed plus whatever, right? So if I plug in pi here, what do I get? But if I just plug in like pi to x cubed, what do I get? It's not a trick question, just pi cubed, yeah? So that's not 0. So I mean your first intuition would be just consider this, right? That should be like the first thing you think of, right? I mean, you need a degree 3, so might as well start with like x cubed, right? And then just try to make it 0. Okay, now this polynomial certainly is not in Q of x, right? I mean, if it was, like pi would be algebraic over Q of x, but this is certainly in Q adjoin pi of x. Yeah. Sorry, not pi. Q adjoin pi cubed of x. Yeah. I mean, it is in Q adjoin pi, but that it wouldn't be degree 3 then. So it certainly is in here, right? Q adjoin pi cubed of x. Does everyone follow? Yeah, so this is, so you know how elements in here, Lola, these are like rational functions in pi cubed, right? So just like, I guess the reason you were confused with like this thing was because I didn't tell you how elements look like. I mean, I just said functions, but I sort of assumed you knew. So, let me just write it out then, right? It looks like, it looks something like this, right? So b1 pi q plus b2, what's the next one? Pi to 6, right? It looks something like this, right? Where uh, c0, c1 pi cubed. Elements in here look like this, right? So you sort of see like we don't really contain pi, because I mean if we did, it would factor, right? And we need degree 3, so we need irreducible. So we need all the factors in here to be not in our field, right? So we want this to be irreducible. And and you all know for a degree 3 polynomial, irreducibility means you know, no roots, right? So, but you all know the high school formula, this thing. Yeah, what is it? I think it's something like this, right? Yeah, so this is x minus pi and x squared plus pi x plus pi squared. Right, so pi is certainly not in here because you only have multiples of powers of 3 of pi. And so it certainly factors like this, but it doesn't, so this is not in q adjoined pi cubed of x. Yeah, so we are done. Yeah, like this because pi is not in there. So this thing is irreducible over, I have to say over what field, right? Q adjoin pi cubed. Yeah. So if you thought it was this, right, instead, this is wrong because it would be degree 2, right? So because x cubed minus pi cubed, this would factor as x minus pi, x squared plus pi x plus pi squared. And and like these are certainly elements in here, right? Both of these are certainly in q adjoining pi because you contain pi, right? So both are elements in here. So this thing, and then you could show this thing's irreducible. So this would actually be degree 2, right? I mean, in fact, like it's degree 1 because pi is a root. Yeah. So this is not what you want, right? You want q adjoin pi cubed. Is everyone clear on this? Kind of. I mean, it's the same idea as this, right? I guess I think the field is just making you fun, making you think twice, right? Like this thing is irreducible because you know it just factors as this, but I is not in R. Yeah. Same exact thing. Like you know it factors as this, but pi is not in q of pi cubed. So you would say x squared plus 1 is irreducible, right? So same exact argument here. It's just your fields are just different. Does that make more sense, or unless you could tell me which part you're confused on? Okay. Let's do one last thing. So let's do 30. So this is interesting. Let E be an extension of finite field now. Finite field. Yeah, for f of alpha, just go back to here, right? So case 1, it looks like, I mean, it's a field, right? Because you quotient out, and then use the theorem to figure out what it looks like. And then case 2, it just looks like rational functions. So okay, so here is where we will use case 1. So where F has Q elements, let alpha be an E algebraic over F of degree n. Prove F of alpha has Q to the n elements. So this should be very quick from the theorem I gave you. So from that theorem, how do elements, if beta is in F of alpha, how does beta look like? Can anyone tell me? So it's degree n. So the irreducible polynomial is of degree n. So how can I express beta? Using that theorem I just told you about like 25 minutes ago. Linear combination of what? Should I go back to the theorem? What does this say? No. Functions of beta. Like beta, if beta is in F of alpha, how can beta be expressed? It's algebraic, right? Where the problem tells you it's algebraic, so you're not in the transcendental case. It looks like linear combinations of alpha, right, up to degree n minus 1, right, where coefficients are in F. Yeah. So I know that beta looks like A0 plus A1 alpha. Sorry. A n minus 1 alpha to the n minus 1. Everyone agree? And now this is just counting argument. How many choices of A naught do I have? So I have all AIs are in F, right? So how many choices of A naught do I have? Q, right? Because F is a finite field of Q elements. And then how many choices? Hopefully you see the answer. Choices of A1. Like Q again, yeah? And then AN minus 1, it's Q. So how many Qs do I have total? Yeah. So if I multiply it all out, I get Q to the n. Yeah. And you're done. It has Q to the n elements. So that sort of motivates you. So I will tell you all finite fields have prime power order, and you sort of seeing why, right? I mean, it's not. I didn't show you this one way, right? So you start off with like Z mod PZ. That's a field, right? Where Q is P. Just think of Q as P, and then from here, it sort of shows that like you can get fields of order P to the n, right? So you might start wondering, are there fields that are not prime power order? And it turns out there's not. Like all finite fields are either infinite. I mean, all finite fields are of prime power order, or it's like an infinite field. Yeah. So there's no field of like order 10. Yeah. 2 times 5 is not a power prime. But so this hopefully this sort of gives you an idea of like at least one direction. Like, is everyone clear on this? Everyone understanding the definition more? So yeah, I'll do more examples next time, but hopefully you're understanding these field extension stuff. Okay, I will see you all Tuesday then. Yeah, Tuesday. Monday, Wednesday stuff, I think. Should be like, I don't think it's that hard. I made the quiz this time, at least the free response. All the multiple choice stuff is already pre-made by the professor, so I have no choice on that. So I did make the free response this week, and if you watched my lecture videos, you should know how to do it. uh, not lecture videos, my discussion videos. Yeah. Okay.